Hi, in this video, we want to look at transforming numeric variables using the exponential group of transformation. So here I'm talking about the Box-Cox transformation, the Yo-Johnson transformation, and the exponential transform. All right, so what we need to think about here is that my goal is to transform my predictor variables so that they will do a better job as predictors in linear regression. All right, now why do I say linear regression? Well, good data prep for linear regression is good data prep for any model structure. So if I have a neural network, if you look at it, a neural network is actually kind of like, I think of it as a tangled bag of linear models, maybe like generalized linear models. There's things like perceptrons and activation functions and link functions, but still fundamentally, it's behaving like a linear regression model underneath the hood. When you talk about neural networks and you hear something called weights, well, weights correspond to coefficients in linear regression. Bias in neural networks correspond to intercepts in linear regression. So because of this, because of that structure, if I do good data prep for a linear regression model on my predictors, I'm doing good data prep for a neural network. Now, other model structures will work out the same way most of the time. With tree models, anytime I have a monotone transformation, it's not going to change anything because of how the cuts are established, if I'm doing like binary cuts. Actually, it doesn't even matter what type of cut we're doing. It could be 2, 3, 4, but almost always it's a two-level split. All right. Now, other formats, k-nearest neighbors, usually will perform better if I do linear regression goal data prep. So in this video, we're going to look at methods to improve our models. All right, so what we're going to do, we're going to apply some kind of exponent or exponent-like model or transformation to our numeric data, and with the goal of improving our data for the purpose of linear regression. If I improve my data for linear regression, I'm probably improving it for other model structures. And therefore, I can just use, I could use like linear regression to evaluate, have I improved my data for modeling? All right, so we're going to use Box-Cox. That's very well known. Now, this will work with only positive values. Yo-Johnson is similar to Box-Cox, but it expands the possible range of values. And then there's the exponential transform, which is really just going on and putting an exponent on there. And it's simpler. My experience is that Box-Cox usually performs best, then Yo-Johnson. And I really haven't used the exponential transform because the other two have worked out for me. All right, so here for the example, let's go ahead and load the data. Now let's go ahead and just clean it up. So I'm using the Nashville housing data set from Kaggle. And I'm cleaning up the column names. So through here, I'm cleaning up the column names. So things are a little bit easier to work with. Syntactically correct column names are very important to use when I start modeling, especially in the caret package, because in caret, what is happening most of the time underneath the hood, another function is being called. Well, if that function assumes that you have syntactically correct column names, you'll have problems. So before you use the caret package, make sure you have syntactically correct column names. And the make names function will always do that for you. But I go a little bit further, I clean things up so what make names does, if I have like a punctuation character, if I have a special character, it puts a period in that spot on the name. And excuse me. And that works out very well. But if I have like spaces and special characters in there, I can have a string of periods, which in this case I will if I look at the actual data set. So the make names cleans that up into something a little bit easier to work with. And then I go through here and I get rid of consecutive dots. Now here I'm getting rid of useless columns. And here I am sorting the data by the number of missing values. And I like to do this before I do imputation. That way, if I want to, I could impute model-based column by column using columns on the left. All right, so now let's go ahead and take a look at our predictors. So here, I'm only going to talk about the numeric ones. I'm not talking about categorical data in this situation. Here are the numeric predictors in the data set, and the data that we're interested in predicting is the sale price. Okay, well, if I look at that, that's financial data. Anytime I have financial data, I expect it to be skew right. This data is skew right. So I go ahead and I hit it with a log transform. And then I subset the data with the predictors to get X as my predictor matrix. The caret package performs better if you supply only the predictors and along with the target variable. All right, so now let's build functions that perform the variable transformations. The reason why the caret package is so good to use is that it doesn't actually transform the data right off the bat. What does it gives us a function so that we can use that function to transform data. Well, if you're paying attention, be like, hey, wait, isn't that an extra step? Well, yes, but here's the magic. Here is the magic to it. What happens is that when I get new data down the road, I need to transform and predict on that new data. So I don't have to retrain the whole thing. If you look at other transformation functions, other prediction functions, other model building and imputation functions throughout R, what I have to do if I get new data that I need to predict on, I have to retrain my model, including that data. I don't want to do that. That is redundant. I don't want to do it multiple times. And this is especially true for the imputation functions, especially like the mice package and Miss Ranger. Well, what caret does instead, it doesn't give us data, it gives a function to apply to the data, and then we apply that function onto the data we're working with. Okay, so the preprocess function, what this does, this gives us a function that takes our data and transforms it based off of the training data set. All right, so for us, this X and Y are the training data. I'm going to pass X and Y into the preprocess function, and then I'm going to tell it how do I want to prepare this data. Specifically, it's going to be working on the predictor matrix. Now, some of the options inside preprocess will use the target variable if I provide it to improve the output. A lot of them don't need it. A lot of them will work with or without. You'll get the best result possible if you include that target variable. All right, so here what I'm going to do in every single example, I'm going to get rid of zero variance columns. I'm going to get rid of highly correlated columns. We're going to do median impute. We're going to center and scale. So I'm just running through this because this is like standard data preparation for machine learning. Now you'll notice that at no point am I doing any exponential transforms on my data. So I'm calling this function the none function. Okay. Now for the box cocks, I'm doing the same operations I did here, but I'm including box cocks. Now something I want you to pay attention to is the order in which I have these methods. All right. In caret, what it does, it has a predefined order by which it does the preprocessing. It will always do the filtering of variables first. So if I do zero variance or near zero variance removal, it does that first. Then it does highly correlated variables get filtered out. Then it does the numeric transformations. Then it does imputation. Then it centers. Then it scales if I ask it to do all these things. Next step, if I asked it to, it would do principal component analysis for me. But I'm not asking that, so it's not going to do it. Now on the next one, the next function, which I'm going to call Yo Johnson, I'm going to include that transformation in the flow. And notice where it is. Once again, it's between the correlation filter and imputation. And then the next function we're going to define is that this is the exponential transform. All right, so one thing to remember is that the output for each of these is actually a function. It's not actually a data set. If I want the actual data, I have to pass the data to this newly defined function. And I get some warning output. So if I get an infinite value for the exponent, caret is just going to say, hey, that cannot be right. Don't do it. Kick it out. All right, so now let's go ahead and look at the transformations that these do for each of them. So I look through, and for none, it's going to center and scale 8 of the variables. It's going to impute 8 of them, and it removes 1. If I look at boxcocks, well, I have the same thing as I had before, but in addition, there are 4 boxcocks transformations. And those 4 are going to be going under the boxcocks transformation with transformations negative 0.4, negative 0.1, 0.1, and negative 2. All right, so now when I look at this, if I was doing this in, like, let's say I was having a project where I had to explain what was going on, I would probably change this to negative 0.05. So, square root, negative square root exponential. Here, I might consider going with 0, and here I might consider going with 0, which corresponds to the log transform. Why would I do this? Well, anytime that I do something in statistics, if there is a nearly equally good version that is easier algebraically to interpret and understand, that's probably the better way to go. So I would strongly consider, if I was doing this by hand, using log transform for these 2 variables. Now, to know which 2 these are, I have to actually print out actual output from the boxcocks function. Now for Yo-Johnson, similar story, center 8, ignore 0, impute 8, remove 1, scaled 8, and then it's doing the Yo-Johnson transformation on 6 variables. Now remember, the boxcocks transformation can only take positive values. If there is a 0 or a negative anywhere in the data, ours is going to go, nope, not doing Yo-Johnson, not doing boxcocks. Yo-Johnson will take a wider range of values. I think it'll take negative, I can't remember 100% off the top of my head. And now here are the 6 exponential values, or the 6 parameters for the Yo-Johnson transform. So here I would be thinking that I would consider like maybe log, because it's close to 0, log. Now here I would probably consider like negative 1/3, negative cubed root. I would consider 0, negative 3, and then here I would consider 1/3 if I have to explain what's going on to stakeholders, to decision makers. And now for the exponential transform, same story, except for this time it's accepting 8. So this is willing to transform 8 different variables. Well, how many did we have? Well, let's take a look. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's transforming all but 1. All right, so now if I want to look at the actual transformations, what I can do, I can grab the function itself. So remember, this is a function because it's output from the preprocessed function. And if I put $BC, it'll give me the boxcocks parameters, a little bit of information about it. So here, if I look at acreage, it estimates lambda at negative 0.04, negative 0.4. For land value, it estimates negative 0.1. Looking at this looks skewed to me more than likely. So I would strongly consider using lambda 0, which is log. Oh, hey, here it actually says use log instead. I didn't notice that before I talked about it. Now for total value, I'm looking through. I see that this looks rather skewed to me more than likely. And how am I picking up skew? I'm looking at the range of values here. How far apart are they? How apart are these? I mean, now several orders of magnitude, but this is bigger orders of magnitude. And I'm looking at the difference here. If I see on like the right-hand side that the space between these two and these two, if this space is much bigger, I'm thinking it's probably skewed. If the space here is much smaller than the space between median and third quartile, I'm leaning towards it being skew right, which means I'd want to use the log transform. Now you'll notice that here it's not calling out to change to the log transform. Now for year built, it's estimating a negative quadratic term. Okay. And here I'm not seeing, if I look at the difference between these two, yes, these are like, very different like values, but they're not orders of magnitude different. Therefore, I'm not really that worried about skewness on this data set. Now for the function using Yo-Johnson, it just gives us the output of each of the parameters. So if I was going to be doing this manually, I would probably consider like negative, 0.1 or maybe 0. Here I've got 0.15, negative 0.3, or maybe negative 1/3. Then so maybe around 0 or negative 0.1. I would definitely go with negative 3 on this one. And then I would consider 1/3 on this guy. How does this compare? So we have these are very different. And now when we talk about exponential transform, it's going to call out -2 for acreage, negative 0.4, negative 0.2 for bedrooms. Half bath is -3. Okay. So here we get one of each, we get each of these for 8 of the variables. Now, so far what we've done is we've built functions that will transform the data. We have not actually transformed any data as of yet. So let's go ahead and transform it. So what I'm going to do, I'm going to use the predict function. I'm going to run predict on the function that I built, and I'm going to set new data equal to my predictor data set. And that's going to generate the new process data set for me. So if I was building models in real life and I had a training data set, a validation data set, a test set, and a scoring set, remember train, we build the model on. Validation, we check to see which model is best. Test, we try to get an honest estimate of how the model will actually perform. And score is the data set that we actually make the prediction on. That's 4 data sets. I have to pass each of these data sets into predict with the function that I'm going to use to transform it. So now let's compare the output we get. So here, what this has done, I've ran through each of the 4 data prep functions. I dropped my predictor matrix into these, and that gives me new data. And that data is stored in the list underscore data. Let's compare the results. So what I'm going to do, I'm going to build a linear model on each of these data sets using all columns of my data in the predictors to predict the log of sale value. So here I'm doing the train package, the train function in the caret package. And so this is going to be the prepared data is the X. The target variable of the log of sales price, which I defined Y earlier, is Y. I'm going to say I want a linear model, and I want to evaluate the model based off the mean absolute error. I find that mean absolute error is a better way to talk about error when I present it to non-statisticians. I know that mean squared error is very juicy for hypothesis testing. It's very juicy for inference. But when I talk to regular people, the root mean squared error, what does that mean? Don't know. But if I say mean absolute error, I can say, just when I talk to most people, I just say the average error. And when I talk about error in that context, I'm not worried about the direction. Is it greater or less than the actual value? I just say this is how far off it was. Here's the average of how far off it was. Now, for evaluating the models, I'm going to choose to use cross-validation with a split of 2. Why do I like this? A split of 2, I have 2 data sets. First go, this is train, this is validation. Second go, this is train, this is validation. I like this because in this form of cross-validation, I have no overlap between my validation sets, I have no overlap between my trained data for all the models. And I find that splitting in half tends to actually be faster than other forms of cross-validation because I'm only using 50% of the data. All right, so now let's go ahead and look at the models. All right, so here, when I look at the data set that had no exponential transform, I can see that it's a 0.5 or MAE. Boxcock is 0.47. Johnson is 0.46. All right, so it's getting a little bit better. And then exponential transform is 0.5. All right, so exponential transform did about as well as the no transform method. All right, so for this data set, I know I don't want the exponential transform. So here, I conclude that of these, the best one to go with is Johnson. Now, what I want to do next on this next example, I want to show you that changing up or modifying the data with a monotonic transform does not change the output for trees. All right, so why is this important? This means that if I'm doing my data prep and I don't know what model structure I'm going to use, then I don't have to worry about damaging my tree models. I don't have to worry about damaging an R-part model or conditional trees or damaging a cart model or random forest or stochastic gradient boosting. I don't have to even think about it. I just prep my data for linear regression. Now, because of the linear regression, the under the hood aspect of neural networks, there's no disadvantage to prepping my data for linear regression. So when I do this, I want to make the best data possible for linear regression. So here I'm going to go through each of the data sets. I'm going to build a function that is a conditional tree. So the method in the train function is ctree. I'm going to evaluate the best model possible using mean absolute error. And once again, I'm doing twofold cross-validation. So let's see what we get. All right, so we have 0.46, 0.45, 0.45 as my MAE. When I scroll down here, I see that I get exactly the same statistics for root mean squared error, R squared, and mean absolute error when I consider either no transform up here or the Box-Cox transform down here. As I scroll down, there is a slight difference on Johnson that could be due to round-off error, that could be due to some random number generator that I don't know about. I think it's due to round-off error. There's a slight difference here on the first one, but you know this is so small. The MAE is the same. The R squared is slightly worse, and the root mean squared error is slightly worse, but compared to up here. But it doesn't really change anything, right? I mean, it's just so close that I'm not going to really care about it. Exponential transform, I see the exact same values again. I see 0.69, 0.68, 0.68, 0.69, 0.68, 0.68. Here, my R squared, I get the same values I had previously, and my mean absolute error, I get the same values I did previously. So what this shows with all 4 tree models, based off of different data preparations each, I get the same performance of a tree. In fact, I'm going to get the same trees every single time because of how things work out. In tree-based models, they split the data into two groups. They go along monotonically and they go chop all the data less than this point goes in this bin, all the data greater than this point goes into this bin. Well, that's all I've got for you. Take care and goodbye.